Tell us about Loxodromics and right-angled Artin groups and graph products.
Thank you, and thank you for the invitation as well. So yeah, I want to talk about kind of work in progress with Atelier. I'm hoping that you're not all really sick of rags by now. If you are, then, well, I'm going to talk a bit about graph products as well, which is maybe a tiny bit of variation at least. And what I want to talk about is finding loxodromic elements in these groups. I think that probably most people here know what a loxodromic element is, but I'm going to do the basic definitions just in case there are some people here that don't. So for a hyperbolic space, an isometry is loxodromic if it has unbounded orbits in this space, and it fixes exactly 2 points in the boundary. And there's various reasons to like these elements. We've all been there. One of the reasons is that if we have a group with a nice action on a hyperbolic space and we find a loxodromic element, then this can tell us something about the growth of our group. Simple example, if we have a nice enough action, we find a loxodromic element, we can find another one along another axis, and we can use these to generate a free subgroup. And the nice actions I'm talking about here are acylindrical actions, which I know have been mentioned, but again, I don't think they've been defined. So we'll also define this. So this is an action by isometries, and this is acylindrical. Yeah, sure. So an action is acylindrical if for every constant r, there exists some other constants, L and N, such that for any 2 points in our space that are far enough apart, we get that the number of group elements that almost stabilize both of these points at the same time is uniformly bounded. So basically, this is just some generalization of what it means to act properly on a space. And as I said, you know, if we have this nice action on a hyperbolic space, we find these loxodromic elements, then we know things about our group. But here I don't want to talk about kind of the general acting on hyperbolic spaces case. I want to restrict us to a subclass, and I want to talk about actions on quasi-trees. Probably unsurprising to anyone that knows me. If you don't know what a quasi-tree is, it's pretty easy to remember. A geodesic space is a quasi-tree if it's quasi-isometric to a tree. And one growth result we have in this scenario is the following. So we have our quasi-tree, we have our acylindrical action, then there exists some constants such that for every finite subset of our group, where some power of it contains a loxodromic element, and also we want to assume that it doesn't generate a virtually cyclic group, so that's boring in terms of growth, then we get some lower bound on the growth of these sets. And this lower bound depends on how quickly we find this loxodromic element. So basically what this is saying is that if we have some group that acts on a quasi-tree like this, and if for every generating set you can find a loxodromic element uniformly quickly, then you get this thing that's somehow stronger than uniform exponential growth. This is the idea. And this followed from work by Delson and Steenbock. They had results for hyperbolic groups, groups acting on trees, also groups acting on hyperbolic spaces that's a bit weaker than this statement. Subsequently, there was another result by Fujiwara who showed basically the same thing as this for hyperbolic spaces, but at the cost of having to assume symmetry in this set. And for the talk today, it's important that we don't assume symmetry. We don't want this requirement here. I'm not going to talk too much more about growth. So if that's not your thing, then you're mostly safe. I just want this here as motivation for a reason why we might want to find these elements in such a context. Okay, so what we want is to work in an example of a group which we know has such an action on a quasi-tree. And one known example of this is graph products. These I will also define. So we take a finite graph. Throughout, V will always be the vertices, E will always be the edges. And then we take some non-trivial groups. These are our vertex groups. Then its graph product is the following. Basically, it's just the free product of all of these vertex groups, plus the relations that two elements commute if they lie in different vertex groups, and there's an edge between those vertices. So a very easy observation is this generalizes right-angled Artin groups. And that's just the case where all of our vertex groups are just the integers. And here, as in the previous talk, this is always going to mean the right-angled Artin group, not a general Artin group. So yeah, I said it's a known result that, at least outside of a few cases, these have these nice actions on quasi-trees. And the way you get at this, there's a theorem of Genevois, I believe, which says that if you take a set S, that's just the union of all of the elements in your vertex groups. This is a generating set of your group, possibly infinite. So we can talk about the Cayley graph. This is a quasi-median graph. Now, I'm not going to pretend to be anything even approaching an expert on these, but a vague understanding. Basically, we learned about median graphs last week. These are the graphs where for any three vertices, you can take, there's a unique choice of geodesics between them, so they intersect at a single point. This is your unique median. Quasi-median graph is like that, except your median might be a triangle, basically. So you have 3 points. And then you can pick geodesics between them, so it looks something like this in a unique way. I don't think so. It's fine, Jen. Last week is that if you have a median graph, then these correspond to being the one skeleton of categorical cube complexes. And I have a similar kind of thing in quasi-median graphs. Is again due to Genevois. There's quite a long paper on this topic. But these correspond with crystal complexes. Which are basically like cube complexes you allow triangles like this as well as your square. It's that you get a this is part of your well. This edge, and this edge, and you implicit complexes, they do the same thing. When you come to a triangle, you're in triangle, you need. So one hyperplane, one hyperplane. So these definitely don't behave exactly the same as hyperplanes in cat zero cube complexes. Whenever you meet these triangles, you split triangles, so you can definitely divide your space between the two pieces. But the fact that you have hyperplane and cycloplane allows you to define a contact graph for this space. So for a cube or a prism complex, it's contact graph. This is the graph where the vertices are just your hyperplanes. I mean, I think you can define the hyperplanes without cat zero. I mean, whether the thing that you get out is like nice or not and has meaning, it probably depends on that. So you have hyperplanes as vertices, and then your edges are in the following situation, which is basically that your hyperplanes pass through neighboring edges. So if those two edges span a square, then that would mean that they cross. That's another version you can get. You can just leave that as your edges, and that would be the crossing graph. But here we're also allowing that they're kind of almost touching each other. This is the contact graph. For a cat zero cube complex, it's a result of Mark-Hagen that this is always a quasi-tree. I don't know if there's a general result about this for quasi-median graphs. I don't know if anyone here knows. But certainly in this context, it is true. And there are known results about the action on this. For this. I'll write this down in a second. Yeah, as long as they're non-trivial. You need some conditions, like you'll see in a second. But so before I write down that theorem, I need to give a few more definitions, and I promise that these will be the last ones of the talk. So bear with me. The first is a reminder that a graph is a join if you can partition your vertex set in some non-trivial way, such that whenever you have a vertex in one and a vertex in the other, then there's an edge between them. So in the graph product case, you can see that this is basically, this corresponds to being a direct product, right? You've got all the stuff over here, there's edges, so it commutes with everything over in the other vertex set. Second thing is parabolic subgroups, which were talked about for Artin groups. We have basically the exact same notion here. These are just the conjugates of kind of your standard parabolic subgroups, which are just the groups that are generated by some subgraph. And then very, very final definition, which is that for a subset of your graph product, we have something called various things, but here I'm going to call it the essential support of your set. This is a subset of your vertices, which is minimal, such that your set U is conjugate into that parabolic subgroup, basically. So these are really kind of the vertices that you need to generate this set, and you can't conjugate away from it at all. And then the result that we'd like to use is actually a combination of results from Genevois and Balianas. Try not to misspell anything. So as long as your graph is connected, and we take this same generating set again, so we know that the Cayley graph, this is a quasi-median graph, then the contact graph is a quasi-tree, the action is acylindrical, and on top of this, an element in this group is loxodromic, as long as its essential support is not contained in a join. And this is pretty much ideal, right? You know, you have this nice action on this quasi-tree, and you have this kind of explicit condition on when you can find these loxodromic elements. So this gives us kind of a really nice, easy route into finding such things. And if we can find them, then we can say nice things about the growth. That's the idea. So the first result I want to mention is the following, which is that there exists some constant that only depends on the graph. And I'm going to talk about right-angled Artin groups first, because this is kind of the easier case, and then we'll kind of build on to graph products. Yeah, there exists some constant only dependent on this graph, such that for every finite symmetric subset of your right-angled Artin group, then there exists some element of bounded length such that this element has full support. And basically what that means from a Loxodromic point of view is just that, well, as long as your graph that your support is in isn't a join, then you're uniformly quickly finding a Loxodromic element on the relevant contact graph. This is the idea. And even if you are in a join, then this is telling you that you're finding these elements that are Loxodromic on the factors uniformly quickly. I raised something I forgot to mention, should have said before, is that a lot of this stuff was already known for the right-angled Artin group case before by Kim and Geberde. And they have a version with the extension graph where this all worked well before this. So yeah, you can get these quick Loxodromic elements in your symmetric sets. And this gives you all these nice growth results. In particular, you can kind of work through the cases. And basically what you end up with is that if you have any subgroup of your right-angled Artin group, which includes things like special groups, then as long as it doesn't have infinite center, then you have this thing that is stronger than uniform exponential growth, which is kind of nice. Yes. So it's Loxodromic when this is not contained in a join, because then, so that's the condition up here. Even if it's contained in a join and it's not actually a join itself, then you can just kind of restrict to this smaller subgraph and you find a Loxodromic element on the contact graph associated to that subgraph. There's only a limited number of those, so this is all fine from a growth perspective, basically. Another nice growth result you can get from this, I did promise I wouldn't talk too much about growth, but try to be brief, is that there's a result by Fujiwara that says that for certain nice enough groups, you can look at their set of growth rates and you can put a well order on this. And right-angled Artin groups are nice enough in a specific sense, such that plus this result, you get this well order outside of a few kind of direct product cases, basically. I should mention that the version I have online is a slightly weaker statement than this. Hopefully it will be updated soon. Certainly when I wrote this down a couple of years ago, I wasn't aware of any other result like this. I think there have been a few since. There's a paper by Montse Casaderuth, Ilya Kazajkov, and Javier de la Nuez Gonzalez. I've probably really messed up multiple names there. I apologize. But yeah, they have a paper about small cancellation elements in RAGs and in graph products that came out the same year, and I think it implies similar things about Loxodromic elements. Also Abdul's recent work, which he was supposed to talk about yesterday and then didn't, in kind of cubical groups and hierarchical kind of hyperbolic groups, gets kind of similar things about Loxodromics as well. The way I did this originally was kind of cheating a bit. I went via mapping class groups. This is actually completely analogous to a statement in mapping class groups by Mangahas. She has a result where she looks at any subset, any symmetric subset of the mapping class group. And to any subgroup, you have an active subsurface. This is basically the support of your subgroup. And she shows that you can uniformly quickly generate a partial pseudo-Anosov that has the same support as your subgroup. This is a very nice result. And so basically what I did is I used the fact that you can embed right-angled Artin groups into mapping class groups. There's various ways of doing that. I used a construction by Clay, Leininger, and Mangahas again. You can kind of send it across. You use Mangahass's result, find this nice partial pseudo-Nosov, bring it back. And as long as you check that everything works out nicely, you get something of full support in the right-angled Artin group as well. So it's kind of nice. But I was always a bit dissatisfied by this result for a couple of reasons. The first one was these various tools, mapping class groups, small cancellation, hierarchically hyperbolic groups. These all seem like quite big hammers to hit the right-angled Artin group with. Right-angled Artin groups are really nice combinatorial things. You have this normal form for the elements. You have this kind of combinatorial definition of when you have a Loxodromic element. Right? It feels like there should be a nicer way, more intrinsic to the right-angled Artin group to do these things. The other motivation for this and the other annoyance is this word symmetric, which I felt really shouldn't be necessary overall. The reason it's there is because all of these different methods use conjugates in some way. This is like the classic way of finding a Loxodromic element, right? Is, you have something over here and you kind of conjugate it so you get something that's in some way sufficiently different. You smash them together and you get a Loxodromic element. But my original result about growth that followed from Delson and Steenbock's work, this doesn't require symmetry. So if you can get rid of the symmetry requirement over here, then suddenly you're talking about all of your subsets, which is somehow nicer. Because talking about symmetric sets is really, in terms of growth, the same as talking about balls. Non-symmetric is something extra. You can perhaps think of it as looking at growth in your sub-semi-groups rather than just your subgroups. So yeah, and this is something that I know you can do in hyperbolic groups, but outside of that, I don't know of too many examples. So this was the aim, is to find kind of a nicer way of doing this that allows you to access these non-symmetric sets as well. So no conjugation allowed. And the first result I know of in this direction, it's a result by Carolyn Abbott and Thomas Ng, which is not on the archive, but I've been given permission to talk about it, which basically says that the same is true for all generating sets of a right-angled Artin group. So no symmetry requirement needed.
Well, you don't have like a subset of the right, just
So yeah, so this is the thing, is right. This immediately gets you these nice growth results for generating sets of your right-angled Artin groups. But I mean, the method is kind of exactly the kind of thing I hoped for. It's kind of very nice. It's short. It's combinatorial. It's no geometry involved at all. It's just using these nice things about right-angled Artin groups. If you want to know more, ask Thomas. The only problem is it uses this nice observation about the combinatorics of generating sets of right-angled Artin groups that don't necessarily apply more widely. You can't use this for generic subsets or for subgroups in general. So we wanted something more than this. And kind of the beginning point is an observation that was first pointed out to me by Rick Wade, which is that if you have a subset, any subset of a right-angled Artin group, then for any vertex in its essential support, then you can find an element of length 2 such that it contains this element in its support. And the reason why this is true is very similar to the trick that Anya was using yesterday, which is that you can use actions of your right-angled Artin group on the Bass-Serre tree. So for any vertex, our right-angled Artin group splits as an H and N extension. In which part? Here?
What's the
This? Is that better? I mean, it was still true, but bit useless. So yeah, our group is an H&N extension. Here B, it's just all of the vertices minus this one, and C is the link. All we're doing is we're taking this vertex out and then we're just putting it back in again. The only relations we need are that it commutes with everything in here. This is fine. So we get this action on the Basset tree. If you're not familiar with Basset trees, there's not too much you need to know. Firstly, it's a tree. Clue is in the name. Secondly, if you have a vertex that does not look much like a vertex, the stabilizer of that vertex is going to be a conjugate of this AB. So an initial observation is that the group generated by U can't stabilize a vertex here, because that would mean that it's conjugate into this, but this would contradict the fact that it has B in its support. This is a result of Antolin and Minassian. And so at this point, we're just using an old trick by Serre. This is in the trees book, which is that, well, in this scenario, for an element of this group, having a vertex in this support, having this vertex V in the support, is exactly equivalent to being a Loxodromic on this tree, i.e. not stabilizing a vertex. So we'll start off by assuming that everything in U stabilizes some vertex, because otherwise this is just done. Okay, so all of these have some set of fixed points. If any of those sets of fixed points are disjoint, then this is a fact about trees, right? Put them together, you're going to get a Loxodromic element, and you're done. So the only way that this could be not true is if for any two elements, their fixed point sets intersect. But these are convex sets. This is a tree. It's an injective space. And we know that this has the Helly property. We learned about this last week. So that would imply that it's got some common fixed point for all of your elements. So your group is going to act on it with a fixed point, which is a contradiction. That's basically the idea here. As I said, this is in Serre's trees book. So at this point, it kind of feels like it's really not too far away, right? We've very quickly found, at least one thing with a vertex in the support. So all we really need to do is we need to be able to combine these supports in some way. And the way you can do this is by, again, exploiting these actions on Basset trees. Because what does it mean to have an element with full support? It means that for all of these Basset trees associated to those vertices in the support, it's a Loxodromic element. That's all it is. So the result we need is the following. I'm at least not aware of being elsewhere, which is that for every natural number, there exists some constant, such that given the following situation, which is that I'm running out of chalk. Firstly, that we have a collection of trees, T1 up to TS. Secondly, that we have a group acting on each of these trees by automorphisms. And thirdly, that we have two elements in our group, such that for each of the trees, at least one of these is Loxodromic. And what we get is that there's some bounded power of each of these, such that when we combine them, and this is a positive element, this is Loxodromic on all of them. This is a variation on a result by Clay and Ujanek. they do something similar for hyperbolic spaces. The difference is they don't make any attempt to make this, to do this uniformly quickly. They just show that there exists some loxodromic element. And that's the same with a few of these other statements, like this trick over here was used by Manassian and Osin. And again, they were just trying to find that there is a loxodromic element. It's kind of this upgrading of showing you can do it quickly and that you can do it in a positive word. That's the difference. This does, of course, beg the question of, is this true, this bounded version true for hyperbolic spaces? I don't know if you'd want to do that. At least here we had a motivation. It was kind of hard enough already for trees. But the idea is basically that there's only so many things that can go wrong in each tree. There's only so many ways that two elements cannot be a loxodromic if you put it together. And so you need to find some way of avoiding all of those cases simultaneously across all of those trees in some bounded range. Is the basic idea. And at this point, it's basically just a matter of putting things together. You have this observation that you've got some element that contains for each vertex. And this allows you to kind of smash them together and to increase their supports, basically, if you think about the actions on the Basset trees. And so as a result of this, basically we get the upgrade that we wanted. So constant only depending on gamma, such that for every subset of your right-angled Artin group, you can find some positive word of bounded length such that it has full support. And again, this allows you to then upgrade all of these growth results as well, or at least a lot of them. Certainly, you then have for all of these subsets that as long as they don't generate a group with infinite center, then you get this growth property. One thing we don't know is this kind of well-ordering stuff. In the original Fujiwara and Seller paper about well-ordering sets of growth rates, they do this for sub-semi groups of hyperbolic groups as well. They don't assume symmetry. In the later paper by Fujiwara, where he looks at groups of acylindrical actions on hyperbolic spaces, he does use symmetry, but I think the main reason for that is to get the growth result that he needed, which is the one I mentioned at the beginning. I think it's very possible that the rest of it follows through without any need for that. I think it's very possible that you get a well-ordering of your sub-semi group growth rates as well. I also promised to talk about graph products. And basically the idea is you can play the same kind of game with a bit of a restriction, which is that this kind of general statement is not going to be true, at least in this generality. There are just examples of subgroups of graph products where they just don't contain any element of full support. But basically, as long as you avoid those cases, then things still work out. So we can get a similar observation to this one over there, which is that for any subset of your graph product, we need an additional assumption, which is that for every vertex in the support is not contained in the star around this vertex. This is basically the place where it can go wrong. And then what we get is, again, there exists some element of length 2, such that this element is loxodromic on a Basset tree associated to a splitting of this group. So here we're going to have an amalgamated product. So here A, this is this join around this vertex, and B and C are the same as before. So you can't use an H&N extension. It's not quite as nice because, we're not just removing the vertex. It's the whole group that's gone. You have to add that back in. You need that information, which is why you need this group here. And the minor complicating factor from that, and the reason why you need this condition, is that for this original trick to work, you need that your group U, or generated by U, can't stabilize a vertex on this Basset tree. We already know it can't be conjugate into here, same reason as before, but in general, it could be conjugate over here into this parabolic subgroup given by this link. So that's why we need to rule out this case up here. It's basically the reason. But other than that, you just kind of get the same thing. So the previous theorem is true for every subset of a graph product that satisfies this statement. And so again, you can relate this back to your Loxodromic elements. Well, basically, as long as your graph is connected and you're not in your support isn't a join, then you're going to get a Loxodromic element in this quasi tree. And so we get this kind of growth. I should also mention that even if your graph isn't connected, then you're still completely fine, because then you're in a free product, right? That case is the non-interesting case, because then you have an acylindrical action on the associated Basset tree, and we've already seen that it's very easy to find Loxodromic elements in the Basset tree. All the exact kind of growth consequences for graph products haven't quite figured out the nice way of writing that out yet. But yeah, I think it'll basically be something along the lines of, as long as you're not in a vertex group or you don't define a join, then you should have this nice growth. I was actually expecting to get interrupted more. This is a bit shorter than I expected, but yeah, I'll leave it there. Thank you for listening.
So this actually depends on that, or in
For the collection of trees.
let's say the theorem with the theorem.
Which one? This one? Yeah, it just depends. I should have really written V. It just depends on the size of V, basically, of the vertex set. Yeah.
Actually depend on V, or take it down to the dimension, meaning the size of the biggest group. But if you can, then you get the result about special cube complexes depending on the dimension. You find this thing correctly.
Where exactly does it show up? I'm not sure. It's basically how it shows up in here in like the Basset trees, because like it's the size of the vertex set is like it's this part. Effectively, it's like how many vertices you have in the support. Whether you can reduce that in terms of size of cliques, I don't know. I'd have to think about it.
It's worth doing.
Yeah. Okay.
Okay.
I'm hungry.
But nobody leave because Donnie has instructions for everybody. We're gonna get our picture taken together.
Everybody is gonna have to leave.